All right, well, the browbeating continues. And so this is a sort of laboratory talk between myself and Jim Sky and Larry online. So I drew a short straw. So here I am. Now I wanted to talk a little bit about the calibrators. John's here, and of course you see Richard and Jacob, calibrator here. I wanted to talk about this a little bit and advertise it as a great project for Radio JOVE and maybe for other things as well. Just briefly, a history. What's the value for the calibrator, and how we calibrated it in the past, and then this the latest edition of our calibrator from Jim Sky design, but mimicked off of prior design by Flagg and Jim Brown. So, as I mentioned earlier, Radio JOVE started in 1999, and soon after, I don't have the original toggle switch calibrator that Nick built, but by year 2000, we were already thinking about this as a way to compare data. And so here is the calibrator and the bandpass filter that we introduced in 2010 for the original Radio JOVE experiment. You see, 2015 was the custom-built switching spectrographs that it built, and then the funded, NASA-funded calibrators that were built 2017 and 2020. And then Jim has been working on this calibrator to design to build it yourself since 2021. So here's the prototypes, or the automatic calibrators that were funded by the grant. And as I mentioned, Jim's design, along with great work with Larry Dodd, is the piggybacks off of this design. So DIY, the do-it-yourself calibrator. And so that actually came in between our RJ 2.0 and 2.1 iteration of receivers. So, of course, the point of calibration is to make the data more valuable. In our case, scientifically valuable. And what I'm going to be talking about here is an amplitude calibration. You can do things to improve frequency calibration, timing, accuracy. But now those things are fairly easy. And another thing I'll mention that we always talk about in our Radio JOVE meetings or teleconferences is the metadata, the importance of the metadata. So within the Radio Sky Spectrograph software, you have places to put in your location and your aspects of your antenna, or the receiver you're using, whatever. We highly emphasize that as something very important for Radio JOVE experiments or anything else that you're doing. Is a way to make the data more valuable. So here's the Radio Sky pipe, single frequency plots, the original Radio JOVE, and the output from was sort of an arbitrary unit, some measure of the voltage, and it's, digitized by the sound card of the computer. So it was a terrific little design to do it that way. And then those original calibrators then would take that output and convert it to, from this relative scale to an absolute scale. Most of us now know as antenna temperature. And just to remind you, this is the A unit that we use in radio astronomy to convert the data as if the radio source, so the emissions that Ed had mentioned back on Sunday, the JOVE emissions and solar emissions, these are non-thermal radio emissions. So, of course, the higher frequency, you get the emission is dominated by the thermal oceans. These decametric radio bursts from Jupiter or the type 3s, these are non-thermal mechanisms. So moving plasma, moving charged particles in the presence of magnetic field. How do you measure the intensity or amplitude of these signals? Well, you can convert this to what we call an antenna temperature. Right? How big, how hot would a thermal source have to be to give you the radio, the amplitude of your radio signal at the frequency you're measuring? That a thermal source would do. So, because it's non-thermal and highly directed, a thermal source, and Ed showed you that on a Planck curve, the hot object has to be millions of Kelvin to radiate radio emission at that thermal temperature. So, really, there's not a whole lot of thermal stellar radio astronomy done for that reason. We just don't know. So, so we convert data to a antenna temperature. So essentially compare what you receive at the antenna with how hot a resistor would have to be to give you the same signal. So that's antenna temperature. And so the original Radio JOVE in the Calibrator filter, and Jim wrote the software within Radio SkyPod called CalWizard that would take a single noise, calibrated noise source, a single figure, and then use the linearity of the sound card to then generate a calibration curve, essentially, that then will convert SkyPipe data unit into an antenna temperature. And the point there is now, whoever you are, whatever, wherever your observatory is, now you have a unit that you can compare. An absolute unit that you can compare. Now, in radio astronomy, you typically want to take it to the next step and convert the flux density you're getting from the source itself. And that is kind of tricky. You have to know a lot about your antenna and the directivity and other things to convert from, say, the antenna temperature, which is measured at the antenna, versus the flux density, how much energy per time per frequency interval is coming from the source itself. So that's ideally what we should be doing, but it's not absolutely necessary to do that last step for flux density. So this is the, and these are online. If you want to get these manual, the schematics are laid out there. So this was the original calibrator, multi-step calibrator that was designed by Nick and Jim Brown and Jim Sky, the software. And these were designed for the custom-built sweeping radio spectrographs. So as you see, the left-hand and right-hand output into the spectrum. So dual polarization. And again, with the Radio Sky spectrograph software, Jim wrote the software to allow the calibrations then to go to the next slide here, to not only capture the converted data to antenna temperature at, as a function of frequency as well, but also display it on the spectrograph output. So wherever you put your mouse, you would actually be able to read the antenna temperature right off of your monitor. So that was sort of the small upgrade for the MK2 Mark II calibrators. And of course, this allows you then, with the advent of the switch over to the FDR, to characterize those receiver settings to get you a calibration curve that is best you can. So that's the software tool that you can get with the Radio Sky spectrograph, and showing you the steps that take you through. And then you can play with your system to try to optimize this calibration, give you the best dynamic range of your instrument. So again, the do-it-yourself calibrator, the instruction manual, the parts list, and I even have, this a couple years old now, the cost of the parts list, and I got it added up to about $270. You might be able to do better than I did on finding some of these parts. But all that's published, so you can build your own if you want to. We're not selling these as a kit because you can find the parts semi-readily. I do have, this one packed up as a kit because I bought some through grant dollars. And here's the connections for the calibrator, just so you can see the schematic here. The SDR is then, the calibrator allows you the multi-step get a good count curve to convert your data into antenna temperature and to make it more easily comparable to other observers. So again, software is free to download. The parts list and plans are all on the Radio JOVE groups.io wiki page. You've seen the John's kit up in the Drake Lounge, and here's the photograph of one that Jim put together. So it's a very doable project. I say that not having done one, but it is on my list this summer to build one of these myself. But it's a great project for somebody who loves to build things. see. Oh, so I put this slide in here just to show you. So here's some frequency versus time data here, so you can kind of gauge what the background level at this site is. So this sort of medium blue color, there's some frequency variation frequency here, but you go through your steps here and you can almost by color tell what the galactic background is, what your local background is. And at close to 20 megahertz, that background should be about 50,000 Kelvin. That's the background and temperature galaxy. And so with the calibrator, you can easily tell whether your site, your background is 200K, 200,000. You're in a bad site. You're not going to get any Jupiter, most likely, and you're only going to get the strongest solar bursts. So it's the way that you test your site there. And we're nice enough that we'll let you borrow a calibrator. Promise to send it back if you want to test your site before you invest a lot of money in 4x4 posts and putting things up somewhere. You can try it out, see whether your site is good or not. Now, just got a couple more slides here that I want to add to what I said earlier about the new 2.1 kit and this SDR console software and SDR2 SDR console RSS software. So those are the intermediary softwares and software that allows radio sky spectrograph to, again, essentially get the output from the SDR Flagg receiver. And then you can control some of the gain settings and adjust your try to optimize your system to give you the best dynamic range. And I really want to thank Larry Dodd, when he's online here, for all the effort, time and effort he did in getting this all to work, getting the software and Gen 2 all talking to each other. And Larry put together a nice document to guide you through the software setup and going through the calibration settings correct. And then he's even made a YouTube video of that. So that is available on the Radio JOVE website there. And oh yeah, so the same slide I showed before. So now, if we have calibrated data, we can actually say something about these radio fade outs or the solar bursts or the Jovian bursts or ionospheric effects. So it's really taking it to the next level. Doing that calibration or having a calibrator is taking your data to the next level scientifically. And the point is, we hope we do more science. And again, the calibrator, I think, is the way to do it. And I've already said this once before, but I'll say it again for thank you, SARA, for having us here and having a great partnership for so many years. So I'll stop and take questions if you have any. I know Francisco is up for the last talk, and then we can banter it out.
And more collaboration through the years. Tough too.
I hope.
Yeah. So yeah, we got time for questions.
Yeah, Chuck, you showed the calibration being sort of visually applied to the data. Can that calibration curve then be permanently applied to be recorded data that RSS records?
Yes, so if you do a calibration, ideally you should do it daily. But unless you change your site or change your settings, that calibration is probably good. Correct me if I'm wrong here, but I would say for a few weeks or maybe longer. You do need to do it maybe at a minimum monthly, I would say, just because the galaxy, where you're observing in the sky is going to be affected by the galactic backgrounds. That changes, 4 minutes a day, very slowly. So you want to.
And somehow the software does actually apply that curve to dates, but it's doing a visual comparison.
Absolutely. So the output is antenna temperature.
How much do trees and vegetation around the antenna affect it? Because you're calibrating the signal at the receiver. The antenna is not in the picture when you calibrate. You got an antenna that's got a lot of trees around it. Your wife won't let you remove them, kind of thing. How much are they affecting? Has anybody done any?
It's a good question. The question is, how much does trees or vegetation around your antenna might affect the calibration at these frequencies? Or shouldn't. I mean, they're not hot, So
you're talking about temperatures in the 50K range versus ambient, for the most part, is in the couple hundred.
Yeah. So it shouldn't matter too much. But that's why the calibrator's in a metal box, and we try to keep the local RFI and other things down, minimize any
Okay, so at least you have a very accurate calibration of the receiver at that point. And
right.
The antenna, I guess they're all constructed by a certain plan, so they should be fairly predictable.
Yes.
Yes.
And at these frequencies, even if your antenna is cut 6 inches too short, it's probably not going to affect things too much. And we've got a huge beam on the antenna, 60 degrees, roughly 60 by 60. So we're not super accurate in where we're pointing, and ground plane does have some effects. So what kind of soil you set the antenna on does matter, but we've never done a thorough study on how that would affect.
Question,
Yeah.
just real quick. Are you guys running Windows 11? And have you tried Linux and Mac software?
The software only runs on Windows. So I think some people have gotten it running on Linux machine. Is that right, Jim? Sabina over in Germany, I thought, had a system running on Linux.
Use a line, Windows simulator.
Yeah.
I think that people have got, I don't know why you would go to that much trouble. We used to take an old throwaway machine and put it on there.
And so, yeah, so you've got to use a Windows emulator, either on a Mac or on a Linux machine. So in that sense, we're not friendly in that regard. I'm going to let Larry jump in and just tell us the dangers of Windows 11. Larry, I know you've got 4 or 5 things you probably could say about Windows 11.
Yeah, I have 3 Windows 11 computers running SDR console and SDRC to RSS, and it works fine, no problems. Early on, Windows 11 had some issues, as any new operating system does, but it has now matured to a stable operating system. A couple of things I wanted to mention that yesterday they started had a conversation about the noise source, and yes, the noise source that we recommend is the Chinese noise source, but there are other sources for the same thing, and it is a reverse diode, reverse Zener diode that is common, and it's available on the internet for the circuit. And Jim Sky has written an amazing software that characterizes this noise source output, and you can see in his software the output level, the dB output level over this 8 megahertz bandwidth that we use, and the characterization software gives you an average dB of that power source, of that noise, and that's entered into the RSS calibration menus to calibrate against the receiver. And so the spectrograph, the blue, dark blue color is relative to 290 Kelvin, and then you have green, orange, red, white at the top at the around 97 megakelvin. So it's calibrated in temperature that way based on a calibrated noise source. So that's the amazing thing of Jim Sky's calibrator.
Yeah, thank you, Larry. I failed to mention that, but the instructions that you get with the calibrator comes with this noise source characterizer, and that Jim has designed, so it takes you through that process.
I'm using it with, I used wine on the Raspberry Pi 4, and using wine I was able to get it to work quite well, but it is basically a Windows system.
Right. So back to the original question, I guess Windows 11 is okay. I thought there were some issues there, but
I'm running 6 machines on Windows 11. No issues for years.
Good.
I keep them up to date. I don't pick up viruses, and I find Windows 11 to be the most solid Windows ever.
that's what you go.
Yes, it's a much more secure software than almost anything else now.
Right.
2 points. First, you only need to calibrate at a single amplitude point. The rest is inherent in linearity with the ADD. B, I give you a functional amplitude calibrator for under $20 a month. That gives you a continuous, not weekly or monthly or whatever, a continuous calibration embedded in your data. So the data can then self-calibrate.
Well, I forgot, what was your name? Jack, as Jack mentioned, but once you calibrate the data, it stays calibrated until you recalibrate it. So it's not like it's just a thing. But yeah,
And I'm saying you can be sure of your calibration, irrespective of your calibrable, because it's embedded in your data and is continuously available.
yeah, I understand that there's ways of using the ADC to calibrate the data, but
The A to D is what's generating your data.
right, but I don't know, again, we can talk more about this, I just don't know if he's got multiple kinds of receivers, and maybe I think there's some non-linearity there at the extreme, so how do you handle that?
First place, you should.
External calibrator, I think, is maybe more universal for a project like this.
You may have some bad receivers which are non-linear, and that's a separate issue.
Could
But
be.
for any decent linear, can you go back to where you showed that curve?
Yes.
That curve.
Yeah.
And you had another one where you had some flare at the bottom.
Yes.
Yes. The two actually show two different artifacts, but both of which are obvious and easy to discern. The first one, where it flattened out at the top, you're overdriving the ADC.
Yes.
You shouldn't be doing that.
Yes.
And there's a very easy test to see if you're doing that, looking at the data. The one at the bottom is a mathematical failure on whoever drew that chart, because you have at the low end a addition of the effective noise of the ADD. In other words, what the ADD terminated shows as far as output jitter, doesn't show what number. Right. Combined with the low RF level, right? And you can characterize that noise floor of the ADD, take those numbers and subtract them from your measure data so that you're just getting the RF.
Right, I mean, and that's.
And
one of the
that's
points.
the nonlinear at the bottom.
That non-linear at the bottom is basically due to the plug-in and not just the ABC, but like the SDR plane, mostly it's got a front end with either an attenuator or RF amplifier, usually both. And if you don't get that adjusted right, you will not receive the lowest levels. You will get it output. So the idea is to get that to go to the corner. Right. And if it doesn't quite go to the corner, you're okay because the glass back. So
The noise floor coming from the antenna, and I sing back to what I said yesterday. Noise floor coming to the antenna compared with the noise floor of your system with the 50 ohm termination should be ideally 15 dB above.
you give a what?
The noise floor of the terminated receiver, which is then the LNA noise and the ADD noise all together. That noise floor then measured and then the termination substituted for the antenna. But you're now measuring the noise floor coming from the antenna. The antenna noise should be in the order of 15 dB higher than your internal noise, or else you're losing sensitivity from your antenna.
But keep in mind, we have to adjust. We're trying to get two different kinds of observations. On one end, we want to be very system. And on the other end, we like to catch this high be able to measure these solar bursts this high.
And that's why you want to keep it at 15 dB and not more. Because if you run it at more than 15 dB delta, you are overloading. You run a potential overload.
Well, these are
So that you keep the levels going into the receiver as low as possible without losing the ability to detect weak signals.
And this is something we could do, like, when we do demos over there, just something we
Yeah,
can
let's
close the conversation
continue
on.
afterwards, because we got one
And
more
the
call.
other point is that with the continuous calibrator that I'm proposing, you can fiddle with the gains of the receiver and still have the calibration coming out accurate. In other words, the displayed level of the calibration signal may go up and down if you fiddle with the receiver, but it's still an absolute level, which is giving you an absolute, shall we say, in software units, however you're displaying dB arbitrary, shall I call it. You will know what that is at the input to the receiver. So everything scales from there.
I don't